Simple harmonic motion of simple pendulum. Okay, first we are going to define what pendulum is. What is pendulum called? Pendulum is an object hang from a fixed point so that it can rotate, swing freely backward and forward. And you are going to suspend an object from a fixed point. This is the fixed point object. And you are going to swing it. It will start vibrating, swinging between two extreme points. So this system is known as a pendulum. In your book example, the first example given about the pendulum is trapeze acrobat, swinging trapeze acrobat, like this one. These two people, they are swinging. Let me use blue pen. Okay, so they are swinging about a fixed point. They are attached to that fixed point by ropes. Swinging trapeze acrobat is a physical pendulum. Yes, it's a pendulum. It's a pendulum, but physical pendulum. Why? Why is it called physical? Physical means, in fact, I just explained. You neglect the effect of nothing. You don't neglect anything. So it's a physical pendulum because mass is distributed over a large volume. As you see, it's not just a point mass. These people, these two people, have a very large area. So mass is distributed over a large volume, and also because this mass is distributed over a large volume, they have a very large area of the contact between the air. For that reason, air resistance cannot be neglected. And air resistance has a very important, significant effect on the vibration of this pendulum. For that reason, friction and air resistance cannot be neglected. They have a significant effect. Third, I mean, these two people are very heavy, so you need a very thick rope. Thick ropes. If it is so thick, so it must have a very big mass. So you cannot neglect the mass as well. Rope is thick. Mass of the rope cannot be neglected. You should take the mass of the rope into account. So that's why you neglect nothing. You didn't neglect the mass, you didn't neglect air resistance, you didn't neglect the mass is not a point mass, cannot be treated as. So for that reason, this system is known as physical pendulum. Your book is asking you, these trapeze acrobats are swinging back and forth. So it's periodic motion. We know that because repeated motions in physics are known as periodic motion. That's why swing of a trapeze acrobat is a periodic motion. But is it simple harmonic? Question is this. Your book is asking this question. And they are swinging back and forth. This motion is a periodic motion. Exactly, absolutely. Repeated motion. But is it a simple harmonic motion? Now the question is this. We are going to try to answer this question. But let's remember first, what is simple harmonic motion? It's a periodic motion. It was a periodic motion. However, that periodic motion must be provided by a restoring force. If a restoring force acts on the body of these trapeze acrobats, we are going to search for that force. If a restoring force acts on the body of these trapeze acrobats, so we can say that this vibration, this periodic motion is a simple harmonic motion. That's why first we should search for a restoring force. Is there any restoring force acting on this trapeze acrobat's body or not? So if a restoring force acts on the acrobat's body, this periodic motion must be a simple harmonic motion. But as I said, studying this physical pendulum is not so easy. Instead of studying this one, we are going to study a model, which is known as simple pendulum. Simple pendulum is a model for swinging trapeze acrobat to answer the above question. So we are going to try to answer this question, but we are going to study not this trapeze acrobat. We are going to study a simple pendulum as a model. So now I will define what simple pendulum is. Simple pendulum consists of a mass called bob. This bob is very small, not very large. So this one is the bob, name is bob, which is attached to a fixed string of negligible mass. So it's also fixed to some point. This is the fixed point. And because the string is so thin, its mass is neglected. So we neglected the masses because it's a point mass, it's so small also. And also there is no air resistance because there is no large area of the contact between the air. So air resistance is neglected, mass of the string is neglected, and pendulum's bob is so small in just a point mass. So that's why all these results as definition of the simple pendulum. This vibrating thing is a simple pendulum. Now we will search. The vibration of this simple pendulum is a simple harmonic motion or not. If we say yes, then we will result. Vibration of trapeze acrobat is also simple harmonic motion. So let's start. We know that vibration of the mass spring system was a simple harmonic motion because there was a restoring force acting on this mass, and two properties must exist for restoring force. One of them is it must be parallel to the direction of the motion, but always points towards the equilibrium position. So in the opposite direction of displacement is like this, its direction is like that. If displacement is like this, direction must be direction of restoring force must be opposite. Yani restoring force must be in the opposite direction of the displacement first. Second, it must be proportional to the displacement. Yani as the mass displaces away from the equilibrium position, restoring force magnitude must also proportionally increase. And displacement of the mass spring system was measured by the distance from the equilibrium position. So we measured the distance from here to there, centimeter or meter. So we said that this displacement of the mass is expressed by distance, which is in meter or centimeter. But simple pendulum's displacement is measured also by the distance. I mean, this distance is also representing the displacement from the equilibrium position. This is the equilibrium position, but mostly displacement of the simple pendulum is expressed by angle, theta. This angle is representing the displacement of the simple pendulum from equilibrium position. Most of the books are writing this one, but your book also added distance. Yes, it is correct to some extent, but we always prefer to use angle as displacement for pendulum's bob. So now let's start. Mass spring system vibrates in the straight line path. Yes, we know this. It's moving a straight line path. Direction of the motion is along the x-axis. And restoring force is also acting along the x-axis, but in the opposite direction of the displacement. But in here, in simple pendulum, case is a bit different. In simple pendulum, especially for large angles, path followed by the pendulum's bob is not a straight line, it's a curve. So as you see, this is a curve. But look at the previous one. So in mass spring system, it was a straight line path. So the one difference is that for large angles, the path followed by the pendulum's bob is a curve. For large angles, motion of the pendulum's bob is not simple harmonic. But as angle decreases, now follow what's happening as angle decreases. So this curve approaches to a straight line path as you make this angle smaller and smaller. Now, for quite small angles, your book says less than 15 degrees, the path followed by the pendulum's bob, almost, not perfectly, but almost a straight line. For that reason, motion of the simple pendulum can be considered to be simple harmonic for angles less than 15 degrees. In fact, this is one way we can get at what angle, how is it simple harmonic or not. We are going to search to the path path must be very close to a straight line. So in this case, we can say that, yeah, it can be, there can be this vibration can be a simple harmonic motion. But in fact, we are not going to search for this. We are going to look for what? Restoring force. There must be a restoring force to make a vibration simple harmonic motion. Now I am going to search the forces acting on this pendulum's bob, and I will try to find a restoring force acting on this pendulum's bob. So let's draw the forces, because only proof, I mean the scientific proof, which can tell you that a vibration is simple harmonic motion is to look for a restoring force. And we know that restoring force must pull the object back to the equilibrium position always. There are two forces acting on the pendulum's bob. One of them is string. There's a string. Of course, this string must act some force, tension force. Remember, we said that. And this tension force always acts along the string on the pendulum's bob. Second force is gravitational force. Earth pulls this pendulum's bob down towards the center of the Earth. Two forces are acting on pendulum's bob. But one force cannot be never be restoring force in here. Which one is this? Tension force. Why? Because tension force is perpendicular to direction of motion. However, remember, restoring force must be parallel to direction of motion, not perpendicular. The one which is perpendicular is called centripetal force. We studied in section 3, chapter 1. Yeah, Ft can provide centripetal force, but not restoring force. Because at every different position of this pendulum's bob, you are going to observe that this tension force is always perpendicular to the direction of motion. That's why tension force is not a restoring force. What about Fg? Now we are going to search. There's one force left, Fg. So I'm going to locate this system in XY coordinate system now. And I know that Ft is always acting along the string, and that's why always perpendicular to direction of motion can never be restoring force. But Fg has two components. One component is Fgx along the x-axis, tangent to the curve, in parallel to direction of the motion, in the opposite direction of the displacement. Oh my God, it gives all the properties of a restoring force. Yes, this is displacement angle clockwise. As you see, Fgx is pulling the object in the opposite direction. Yeah, it's in the opposite direction. Yeah, this Fgx can be a restoring force. What about Fgy? It cannot. Why? Because it's perpendicular to the direction of motion. Just like Ft, these two cannot be restoring force. So Y component and F of the Fg and Ft, they are perpendicular to the direction of motion, so they cannot be restoring force. Only one force is left, Fgx. That's why we will say that Fgx is the restoring force, always pulls the pendulum's bob back to equilibrium position. Now in here you are going to see an animation. Animation writes Gx, but with Gx we are referring Fgx. Now this pendulum is at maximum displacement from equilibrium position, maximum angle. As angle is maximum, Fgx is maximum, but observe that as angle gets smaller and smaller, Fgx proportionally decreases. A second property of the restoring force. One property, it must be in the opposite direction. Yes, it is. When the displacement is in clockwise. So as you see, Fgx is pulling in counterclockwise. Second one is its magnitude must be proportional. Yes, it's proportional. Now observe it. So when it's swinging, how Gx is changing. As it's approaching, as angle decreases, Gx also decreases. Angle becomes 0, Gx is 0. Now displacement is on the right side, Gx is on the pulls object back to the left. So this Fgx is the restoring force which causes the vibration of this simple pendulum about this equilibrium position. And ministry exam question also. Which of the following force is the restoring force Fgx, x component of the gravitational force? The component of the gravitational force which is tangent to the curve. Yes, this is the curve. As you see, Fgx is tangent to the curve. This is the one of the ministry exam question. X component of gravitational force tangent to the curve is the restoring force. So how can I find it? How can I find this Fgx? Here's a right angle triangle. Whatever this angle is theta. That angle also will be theta. So here you see a right angle triangle. And y is this part, Fgx is that side. So Fgx is opposite side of the angle. Opposite leg is calculated by what? Fg hypotenuse multiplied by sine theta. So Fgx is calculated by Fg times sine theta. So x component of the gravitational force is restoring force because it is always in the opposite direction of the displacement. As you see, displacement is to do this direction, but Fgx in opposite direction. Second, Fgx and displacement theta are directly proportional until 15 degrees, because after 15 degrees, this proportionality disappears. That's why your book is telling you that, yes, every book is saying something different, but your book is telling that it is less than 15 degrees. So this proportionality between Fgx and theta are possible. So Fgx and displacement theta angle are directly proportional until 15 degrees, angle less than 15 degrees. And as theta increases, restoring force Fgx also proportionally increases. And its magnitude is calculated by Fg sine theta. Fg we know equal to m times g. Sometimes they can ask you directly this equation they asked in 2019. This one, which are the following equation, is the restoring force is mg sine theta. In one of the exam they ask which are the following is the restoring force for simple pendulum. I said master principle, I think simple pendulum, which is the component of the gravitational force tangent to the curve. This is another question they ask, but two questions I ask about this restoring force of simple pendulum. So then, if only the angle of the displacement is relatively small, less than 15 degrees, the vibration of simple pendulum is simple harmonic. Can we say the same thing for trapeze acrobat? Yes. For swinging trapeze acrobat, if the angle of displacement is less than 15 degrees, that vibration is also simple harmonic motion. Okay, questions?
Teacher, if the angle was bigger than 15 degrees, is there still a restoring force?
No, restoring force must be proportional to the angle. As angle gets bigger, this proportionality disappears.
Okay.
That's why for angle, I mean, your book is saying 15, but some scientific books takes the until 12 degrees. I mean, there is no absolute limit, but as angle is closer to the zero, closer to the angle which is zero, like two angles, compare them, 5 or 10, which one has a perfect simple harmonic motion? 5. Because as angle gets closer to the zero, this proportionality becomes, I mean, the perfect compared to angle which is greater.
Also, what if it asks you like if the angle was 15 degrees exactly? Could
no,
it ask
they
you this
cannot.
Question?
There is no such a question. Less than
Okay.
50. Your book is saying less than 50. People learn that way.
Okay, thank you so much.
You can never say your angle of 15 degrees. No. Less than 50, there are some specific questions, and when you check the ministry exam question, you will see that. So for angle theta, less than 15 degrees, so your book accept that motion is simple harmonic motion. For for mass spring system, we have elastic potential energy, remember? But in vibrating simple pendulum, we have gravitational potential energy. Only difference, in fact, is all other things will be the same, Because these pendulums gravitational potential energy is changing as it is swinging. We have at lowest point of this pendulum's bob. This lowest point, I will say 0 level. I'm in the floor. You can think it's a floor. So at this zero level, gravitational potential energy is minimum, or you can say that's 0. But as it is rising, as this pendulum's bob is rising, as height is increasing, remember gravitational potential energy equation, which is mgh. As h is increasing, gravitational potential energy increases. That's why at maximum displacement from equilibrium position, just like mass spring system, because in mass spring system, elastic potential energy was maximum, but in here and right here, gravitational potential energy is maximum. But at equilibrium position, because it is at 0 level, gravitational potential energy becomes 0. But kinetic energy is reverse. In here, kinetic energy is 0. In here, 0 because object stops, pendulum bob stops. But at equilibrium position, the pendulum bob passes from equilibrium position with maximum kinetic energy. So then, gravitational potential energy of the pendulum is 0 when it's at the lowest point of its swing, which is known as 0 level. At equilibrium position, its gravitational potential energy becomes 0 because it's the lowest point. As pendulum bob displaces away from equilibrium position, as it is rising, its gravitational potential energy increases, but kinetic energy decreases. At the end, at maximum displacement from equilibrium position here and here, so gravitational potential energy becomes maximum, but kinetic energy becomes 0 because mass stops. So I'm going to show them on a diagram. First position is, this pendulum bob is swinging like this. I draw it a little bigger to make you visible because normally this angle is not acceptable for simple harmonic motion. So at 1 degree at the first position, which is the maximum displacement from equilibrium position. So because the pendulum's bob is at rest, kinetic energy of the pendulum is 0. This bob's kinetic energy is 0. Because it's rising the highest altitude, h maximum, so pendulum's energy in here is completely gravitational potential energy at the first position. Then when this is released, when this pendulum bob is released, it starts swinging towards the equilibrium position. So altitude, height decreases. As height decreases, we know gravitational potential energy decreases. System loses potential energy. However, this time it speeds up. It speeds up as it is swinging towards the equilibrium position. V increases. If V increases, kinetic energy starts to increase. So it gains kinetic energy but loses potential energy. But at equilibrium position, at the third position in here, it is the lowest point. So in here, velocity is maximum, kinetic energy becomes maximum, but potential energy becomes 0. Then it starts rising again. It starts rising again. So as it is rising, speed slows down because velocity starts decreasing, kinetic energy starts decreasing, but gravitational potential energy starts increasing. So at the fourth position, as pendulum swings past its equilibrium position, the kinetic energy decreases while gravitational potential energy increases. And finally, at position 5, it is another maximum displacement. In here, pendulum bob stops. That's why kinetic energy becomes 0, but gravitational potential energy gets its maximum value at maximum displacement. This is how gravitational potential energy and kinetic energy of the pendulum's bob is changing as it is swinging back and forth about equilibrium position. And remember, I told you that kinetic energy and gravitational potential energy, some of them is called mechanical energy, and this sum always constant if there is no loss of energy, if you neglect a resistance, if you neglect the friction, so sum of the kinetic energy and potential energy of a system always constant. That's why mechanical energy of this swinging pendulum will stay constant. If I draw a graph which indicates how energy and displacement of the pendulum's bob is changing, we know that at negative x max theta maximum, remember we measure the displacement by theta. This is negative theta maximum in the left side. So in here, the kinetic energy is 0 because pendulum bob stops. Kinetic energy is 0. I am going to determine, put a point in here. This is kinetic energy, which is 0. But potential energy at this position becomes maximum. So potential energy is maximum. So for that reason, I will represent the potential energy with the red dot in here. So potential energy is maximum, but kinetic energy is 0. However, at the swinging towards the equilibrium position, potential energy decreases. Yani this red line will approach to the 0 slowly. As you see, it's decreases. But kinetic energy is increasing. At equilibrium position, what happens? Kinetic energy becomes maximum. Kinetic energy becomes maximum. This blue is maximum. But gravitational potential energy, because it's the lowest point, becomes 0. So then on the right side, it starts rising again. What does it mean? Gravitational potential energy increases, as you see, gravitational potential energy, but kinetic energy decreases and becomes 0. So this graph is representing how kinetic energy and gravitational potential energy of a simple pendulum is changing as it is swinging back and forth. But be careful. Some of the kinetic energy and potential energy, which is total mechanical energy, never changes. It is always constant because no friction, no air resistance. And then there is a table, summary table. In fact, this table, the table which is about the mass spring system, is exactly the same. Only difference is instead of elastic potential energy, simple pendulum has gravitational potential energy. Only difference is that all other things in this table exactly the same as how restoring force, acceleration, potential energy, kinetic energy, and velocity of a mass spring system is changing. So remember, I told you that these three from the same family, and always they will change together. What are they? Restoring force, acceleration, and also gravitational potential energy. So when at maximum displacement, they all maximum. Restoring force is maximum, acceleration is maximum, gravitational potential energy is maximum. And again, on the other side, again, positive x maximum displacement, restoring force is again maximum, acceleration is again maximum, and gravitational potential maximum as well. But kinetic energy and velocity, they are from the same family. These two will change together. So while other three are maximum, these two will be 0. At maximum displacement, both kinetic energy and the velocity of the pendulum's bob will be 0. On the other side also they will be 0. But at equilibrium position, so restoring force is 0, acceleration is 0, gravitational potential is 0. However, kinetic energy and velocity are maximum. As I said, if you know this table, you will know the table about mass spring system exactly the same. Only changes what? Instead of elastic potential energy, we have in here gravitational potential energy.